Welcome to the Security Report addressing CWE 347, Improper Verification of Cryptographic Signature. My name is Aspen Call.
My name is David Gang.
In this report, we delve into the details of CWE 347, focusing on its impact and how it can be detected, prevented, and mitigated. Let's get started.
So, the CWE is listed on the OWASP Top 10. CWE 347 is when the product fails to correctly verify cryptographic signatures for data. It's not a new weakness technically, but it was renamed and then moved up one rank. The reasoning is probably due to the widened scope of what is considered in its category and is not listed on the KEV.
CWE 347 is listed under the Cryptographic Failures section, which is the category for failures or a lack of cryptography functions or features. You can prevent this weakness by ensuring that the product correctly verifies the signatures, prevents this weakness from occurring. And an example of this weakness is a downloaded jar file is used to create a new object. The downloaded file was never verified by the system for whatever reason. The file may or may not be malicious.
So CWE 347 is a base weakness. Base weaknesses are when it's still abstract but has been sufficiently defined with enough ways to determine how you'd prevent or detect it. It needs at least 2 or 3 dimensions to describe the error out of the categories of behavior, property, technology, language, and resource. Using more or less than 2 or 3 will change what it is classified as.
CWE 347 is a child of CWE 345, which is insufficient verification of data authenticity. This weakness occurs when the product does not verify the origin or authenticity of data in a way that causes it to accept invalid data. This makes CWE 347 a weakness of CWE 345, since it is more specific in that the product does not verify the origin of cryptographic signatures.
So there's not that many listed occurrences of CWE 347. In total, there are 4 listed, 2 from 2002 and another 2 from 2005. Both the 2005 instance occurred on voice over IP phones, not properly checking caller ID, branch, and tag values in notify messages, which meant that attackers could spoof the numbers. For the 2002 incidents, one incident was in an HP LaserJet printer, and multiple versions of HP LaserJet printers, and allowed users to load unauthorized services. The other incident was on specific Cisco routers and allowed attackers to modify DocSys settings via a file as it lacked a message integrity check. The likeliness/frequency of these attacks were not listed, though. And on the next slide, we have a few pictures of what these weaknesses were on. As for the security consequences, confidentiality can be easily compromised as the product system does not correctly verify signatures, which means that accidentally downloading or executing some more serious threats could directly harm the user's confidentiality. As integrity, the integrity of the product is directly compromised as the system no longer properly functions as it's supposed to, which opens up a possible venue of attack or malicious actors to do greater damage by exploiting this. And the availability is also at risk, as the product can be compromised through the weakness if the weakness is used to, again, exploit a greater threat that could interfere with the availability of the product.
One weakness example is a user decides to download a driver update from the internet. They unfortunately download it from a shady website posing as the manufacturer, and since the computer fails to verify the cryptographic signature, it fails to detect that this file is coming from a suspicious source. Next example, a user's phone fails to properly check an incoming caller ID. This, along with several other failed checks, may mean that the incoming caller is able to spoof a number to trick the user into thinking they are a different number.
For exploitation, physical access is not strictly needed to exploit this weakness, as the weakness is design or execution issue that occurs in the program or product side when its own system fails to properly execute without physical tampering. The attack can be done entirely via software, as there's no need for physical access to the device, and the weakness occurs in the product's execution and subsequent failure to actually check the signature of what it's doing. The weakness is possibly, depending on the implementation of each of the devices, applicable to family devices. If the implementation of a verification is same or similar across a wide range of the products, the flaw will probably propagate through each of the versions if left uncorrected. But if they differ enough, it probably wouldn't.
The only suggested method of detection that is listed is automatic static analysis. Besides that, the frequency of detection from products before fielding or during design are not listed, but there are 4 entries for detection after products had been fielded, 2 in 2002 and another 2 in 2005. There are no explicitly listed mechanisms for the prevention of this weakness, but general programming guidelines are effective methods to aid in preventing mechanisms, such as rigorous testing and reviewing the code to ensure that the function responsible for verifying the signature functions correctly. Some methodologies to help detect this weakness could include risk assessment, static analysis, and monitoring for weaknesses, as these will all catch or minimize the weakness before it becomes exploited. Again, there are no explicitly listed mechanisms for the mitigation of this weakness, but careful review and testing during the design and implementation phase can ensure that the weakness is caught early on before fielding. The weakness can be mitigated once fielded with a software update. A hardware modification is not necessary, as it is just fixing or adding a verification mechanism of the signature.
For the related CVEs, CV 2005 2182 was the Grand Stream Budget Tone 100 voice over IP phones did not properly check the ID, color, branch, or tag values for notify messages, which resulted in remote attackers being able to spoof messages. The solution is that phones who receive a notify message to which no subscription exists must send a 4881 subscription does not exist response, and no remedy was listed for this particular incident. For CVE 2002 1796, the Chai VM Easy Loader for HP Color LaserJet 4500, 4550, 4100, and 8150 did not properly verify jar signatures for new services, which meant local users were able to load unauthorized Chai services. It is unknown how this vulnerability was detected, and there has been no explicitly stated solution.
In conclusion, the examination of CWE 347 has shed light on critical vulnerabilities arising from the improper verification of cryptographic signatures. It's important for developers to prioritize implementing cryptographic signature verification mechanisms in order to prevent malicious attacks. As technologies continue to evolve, it is more crucial than ever to remain vigilant in addressing vulnerabilities like this one.